Assalamualaikum warahmatullahi wabarakatuh. Today I would like to present our topic is ECG QRS detection algorithm based on CNN with Wavelet transform enrichment, and this is our team members, and this is our problem statement is a heart arrhythmia and objective. The MIT arrhythmia database is used for monitoring patients with arrhythmias and developing algorithm to detect and classify arrhythmic events. I leverage the MIT BIH arrhythmia database for arrhythmia monitoring and algorithm development as a main database dataset containing both QRS and non-QRS events, and use a CNN model to classify images into QRS and non-QRS categories. And this is dataset MIT arrhythmia database. The MIT BIH arrhythmia database, the first standard test material for evaluating arrhythmia detectors, is widely used globally for cardiac research. It's freely accessible on PhysioNet. And database is contained 48 half-hour two-channel ECG recording from 47 subjects studied between 1970, 1975, and 1979, including both common and rare arrhythmias. And the recording were digitized at 360 samples per second with 11 bits resolution. And this is sample dataset labeled as 100.
The first step in pre-processing is QRS peak detection. As seen in the figure, to extract the QRS and non-QRS regions, a peak detection algorithm was developed. By trial and error, it appeared that the optimal window size was 36 samples to cover QRS regions. As a result, 1 QRS and 7 non-QRS images were obtained. For that purpose, the whole samples we used, which are 650,000 samples.
Pre-processing of wavelets. Wavelets decompose ECG signals into frequency components for better feature extraction, focusing on QRS wave characteristics like sharp transitions and energy. We use RBIO 1.1 for smooth changes, DB1 for detecting abrupt changes, and HAR for edge detection. Higher order Dobeshe's wavelets DB2 and DB3 extract detailed features, while SIM3 preserves the ECG's morphology. A decomposition level of 5 captures both low and high frequency details. Next, we have some figures which shows different wavelets used for ECG signal processing. Each represents a unique waveform. RBIO 1.1 and DB1 handles smooth and abrupt changes. HAR detects edges, DB3 and DB2 provide detailed extraction, and SIM3 help preserve the ECG's morphology.
To convert the ECG signal to image, first we extract it and normalize it, then apply wavelet transform, then we iterate to QRS annotations to identify QRS non-QRS regions, then we scan them at 255, convert them to images, and finally we balance them using random sampling. As a result, we get a dataset of two classes with each class has 22,008 images and size 36 by 37 by 3. So these are samples, QRS sample and non-QRS sample. As you see, there are 6 images concatenated which define 6 wavelet types used, and each image there is 5 pixel layer which define the wavelet level used. So this is the model. There are 3 consecutive convolution max spoon layer with ReLU activation function, a flatten layer, a dense layer, then a drop up layer, then 2 dense layers. So for the training, 70% of dataset was used, validation 20%, and testing 10%. Extra is out of sample dataset which has 114,200 people set images. Hyperparameter table contains loss function which is binary cost entropy, best size 256, optimizer Adam, 20 epochs, and limit 1e-5. Now the evaluation, as you see here, the accuracy of dataset is 96.32%, while our sample data is 96.91%.
Visualization of accuracy and loss curves. The graph shows accuracy over 20 epochs for training and validation datasets. Training accuracy starts at 65% and stabilizes at 96.5%, while validation accuracy follows a similar trend with minimal overfitting. The close alignment of the curve shows the model's ability to generalize. Visualization of loss curves. The graph shows model loss of both training and validation datasets. Training loss drops sharply in the early epochs and near zero, indicating effective learning. Validation loss follows a similar trend, confirming no overfitting. The sharp decline in loss, along with high final accuracy, highlights the effectiveness of the CNN architecture and pre-processing. Visualization using confusion metrics. The confusion metric highlights the model's strong performance with high precision and recall for both QRS and non-QRS classifications. The F1 score and average accuracy are both impressive at 96%, indicating effective classification and minimal errors in detecting QRS events.
Okay, for documentation, our key findings is pre-processing dataset requires extensive RAM, adding layers to CNN cause sensor size issues, and imbalanced dataset affected model training. Key binding identified for suitable wavelet transform levels and window size for QRS detection. For the challenges is technical limitation due to high RAM consumption, tensor shapers collapse to zero with certain CNN configuration, models struggle to learn from imbalanced dataset, and difficulty in selecting optimal parameters for wavelet transform and their corresponding levels and window size.
Experimentation with model architectures and hyperparameters showed mixed results. Adding 2 extra layers slightly decreased the test accuracy, while varying the number of epochs resulted in minimal changes, with overfitting observed at higher epochs. Switching the optimizer from Adam to RMS probe improved test accuracy, but introduced instability across different datasets, highlighting the need for careful optimization to maintain model stability. Changing the activation function from ReLU to leaky ReLU improved accuracy, while switching from sigmoid to softmax in the last layer resulted in significant performance drop. These changes led to lower accuracy, indicating that the original activation functions were more effective in maintaining model performance. The references are Arrhythmia, a guide on heart rhythm, for wavelets, comparing different wavelet transforms on removing electrocardiogram baseline wonders and special trends, and for the code, wavelet transform and ECG application in Python. Thank you.